Hi everybody, welcome back. It's Miss Smith again. This video is going to be covering Chapter 5, Section 4, and it's going to be all about valence bonding theory and hybrid orbitals. So Chapter 5 introduces two different bonding theories. One is the valence bond theory, which is what this video will cover, and the other is the molecular orbital theory, which is going to be covered in the next video. So these bonding theories provide descriptions on how bonds are formed in molecules or polyatomic ions. So we're talking about covalent bonding interactions here. This essentially ties together all the energy of electrons and stuff that we learned in Chapter 3 with Lewis structures and shapes of molecules in Chapters 4 and 5. So we're trying to just tie a bow onto all that happy bonding stuff. So again, it's based on the quantum mechanical approaches and the theory that electrons reside or they live in those quantum mechanical orbitals. So again, this one's going to be talking about the valence bond theory, which is it's kind of the easier of the two. Not that the other one's super complex, but it is atomic based and it's easily visualized as opposed to molecular orbital theory or MO theory, as you might hear it called. We're looking at molecular-based orbitals, as the name implies, and it's a little bit more complex, but it describes it a little bit better. But we're going to learn the differences and similarities between these two bonding theories. So in valence bond theory, we're going to be looking at the valence electrons, right? Valence bond theory, valence electrons. And these valence electrons reside in atomic orbitals. So these are the S, the P, and the D. We're not really going to be talking about the F here. Or these new, what we're going to be calling hybridized orbitals. So a chemical bond results from the overlap of these two atomic or hybrid orbitals. So they usually contribute in one electron, and they overlap with another orbital that contains another electron, and you make that pair, and that's what forms your bond. That's what holds these atoms together. So there is a possibility for you to do an empty orbital and a filled orbital overlap, but the main thing here to remember is that the greater the orbital overlap, the stronger the bond, which kind of makes sense. So the shape of the molecule is determined by the geometry of the overlapping orbitals. So this is where we're going to tie together this bonding theory and the shapes that we just learned. Alright, so in these very simple cases, we're again looking at the valence electrons. We've got two hydrogen atoms. Each has one valence electron, and that valence electron lives in the 1s orbital. So when these guys come in close contact, those guys just buddy up to make the H2 molecule or diatomic hydrogen. So you've got a good overlap here. You've got a nice bond. Fluorine can do the same thing, where you've got 2p electrons, or valence electrons here. And we've got, one electron in the 2p, another electron in the 2p. They come close together, make a happy bond, and make the diatomic fluorine molecule. You can even have some overlap. So you've got the 1s electron in the hydrogen atom, and then you've got a 3p electron in the chlorine atom. You've got overlap here, and you make HCl with a happy overlap here. So let's look at the hypothetical bonding in the BeH2 molecule. So here we have the ground state electron filling diagram of beryllium and the two hydrogen atoms. So beryllium is 1s2, 2s2. Hydrogen, we've got 1s1, and the other hydrogen obviously is 1s1. So if we look at the beryllium electron filling diagram, we notice that we've got 2s2, we've got a pair of electrons here. So there's really no kind of impetus for this guy to make a bond. So to do so, we've got to look at the excited states. That's when we take one of these electrons, give it a little energy, and promote it up to the 2p subshell. So this is, again, tying back what we learned in Chapter 3, where we gave electrons energy and they hopped up to the next highest energy level, tying that all in here. So now we have two unpaired electrons in beryllium. So now we can kind of see where maybe we can start making some bonds. But looking at it this way, we can see, all right, so we've got beryllium hydride, BeH2. So it must have one bond that's between the hydrogen 1s electron and the beryllium 2s electron. And then another bond that's, again, with the other hydrogen, with its 1s electron, but then with a 2p electron. So we've got two different bonds that are going to look a little different, maybe. But looking at it that way, if we look up some data on the beryllium-hydrogen bonds, we can see that they both have the same energy and they both have the same length. So they're the exact same type of bond. So what we just did, that relatively simple approach to kind of explaining how these electrons will bond together, can't quite handle even this simple model. So we've got to look a little deeper. So here we're going to introduce the concept of hybrid orbitals. So this kind of reconciles the fact that the orbitals in the molecule aren't quite the same as the orbitals that are in the atom. And this came from Linus Pauling back in the 1920s, and he found that the wave functions, so those little trident-looking guys, those psi's, of the s and the p orbitals, as well as some others, can be combined to form these new hybrid orbitals. And these hybrid orbitals minimize the energy of the molecule by maximizing that overlap. So again, it's just the fact that it makes these hybrid orbitals is just driven by energy. We want things that have the lowest energy. They can make a hybrid orbital, it's lower energy, so it's going to do that. So when we talk about these hybrid orbitals, we cannot forget about our atomic orbitals. So it's all going to go back to the s, the p's, the d's, and the f's. So remember, when you draw your electron filling diagrams, you always draw one s orbital, you draw 3 separate p orbitals, you draw 5 separate d orbitals, and even though we're not really going to go that deep, you draw 7 separate f orbitals. All right, so keep those numbers in mind as we go through. So the number of standard atomic orbitals, if you add them all together, that equals the total number of hybrid orbitals formed. So you can't create new orbitals just because you're combining things. You have a limit. The number and the type of standard atomic orbitals will determine the shape and the energy of these hybrid orbitals. So they still have some characteristics of the atomic orbitals from which they're derived. The names of the hybrid orbitals tells you exactly who makes them up and how many are combined, and we'll see that in the next few slides. And again, all of this is dictated by energy, so you want the lowest overall energy of your hybrid orbitals, and we're going to look to the electron geometry to try to predict our hybrid orbitals. And just because an atom bonds one way and has a certain set of hybrid orbitals in one molecule does not mean that's the only way it can form hybrid orbitals. So especially with carbon, we're going to see that, in one situation, it's going to have this set of hybrid orbitals, and in a different bonding arrangement, it's going to have a different set of hybrid orbitals. So this is just an overview. Keep this stuff in mind. Come back to this slide once you kind of get into the thick of it, and hopefully stuff will make sense as we go through. So the first type of hybrid orbital we're going to talk about is what's called the sp3 hybrid orbital. And this guy is formed by mixing your s orbital and all 3 of your p atomic orbitals. So you get the 1s and the 3 p's, and it makes together a total of 4 sp3 hybrid orbitals. And just a quick reminder to count the total number of atomic orbitals that make up the hybrid orbital, you just add together the superscripts. So there's 1 s orbital, because there's no superscript, and 3 p's, 1 plus 3 gives you 4. So these hybrid orbitals, even though they come from the s and the p atomic orbitals, they are all degenerate in energy. So again, degenerate means that they're all equal to each other in energy. So you make 4 hybrid orbitals, sp3, that are all equal to each other in energy, all on the same level. So looking at these guys, again, we've got the spherical s orbital and then the dumbbell-shaped p orbital. When they all come together, they still kind of hold their dumbbell shape, but one lobe's a little bigger than the other, so it's a little more spherical in nature. So all of these 3 guys come together to make our tetrahedral electron geometry, where we've got 4 areas of electron density around our central atom. And this is where the 109.5 degrees comes from, because maybe you were thinking, okay, well, I've got, s orbitals and p orbitals. I know these p orbitals are 90 degrees apart, so how in the world does that make up something that has bond angles of 109.5? Well, it's because it occupies hybrid orbitals. So sp3, something with 4 areas of electron density around it, makes that tetrahedral electron geometry 109.5 degrees apart from one another. So again, we see this in many different things. So first here we're looking at methane. So we've got a carbon with 4 hydrogens around it. So again, if you draw your Lewis structure, you see that you've got a carbon with 1, 2, 3, 4 hydrogens around it. So this carbon is going to adopt 4 sp3 hybrid orbitals to accommodate bonding with the 1s orbital of the hydrogen atom. The hydrogen atom can't make a hybrid orbital because it only has 1 electron, so there's no mixing to be done there. So we see our hybrid orbitals here. When they draw them out in your book, you notice they only draw the big lobe. The little lobe is still there, but it would be really messy, so you can't really see it. So you make a bond between the sp3 hybrid orbital and the 1s orbital of the hydrogen. You can do the same for ammonia, NH3. So again, if you draw your Lewis structure, we see we have 1, 2, 3, and the lone pair makes 4 areas of electron density. So we know that our electron geometry from the first part of chapter 5 is going to be tetrahedral again. So again, we're going to have the hybrid orbitals, the sp3 hybrid orbitals making a bond with the 1s atomic orbital of hydrogen to make those bonds. And then that last lone pair is just sitting above in its own hybridized orbital. So again, this makes a tetrahedral electron geometry, and that's where we get the 109.5 bond angles from. Another important thing to note here is to see how these electrons kind of mix together. So with carbon, when you blend all of these, the 2s and the 2p electrons together, you've got 4 degenerate hybrid orbitals, so you spread those electrons out. So that's why this carbon will make 4 distinct bonds. You do the same thing for the nitrogen. You spread them all out, but you still have one guy paired up. So this guy's the lone pair, and then the nitrogen makes 3 bonds. So we had sp3, which took the 1s and the 3p orbitals, mixed them all together. Our next up is sp2. So here's where you have 1s electron. And when I say 1s, I'm not saying 1s like hydrogen is 1s. I'm just saying you have 1 individual s orbital and 2 individual p orbitals. And those guys mix together to make 3 sp2 hybrid orbitals. So again, add up the s orbital and the 2 of the p's to get 3 total. Now this does leave 1 completely unhybridized p orbital. So here you've got your 3 degenerate sp2 hybrid orbitals, and then your unhybridized p orbital is left at its same energy. So see, these are kind of mixed together, a little bit lower in energy than the 2p, but a little bit higher than the 2s, so average them out. And then you've got the p orbital left over. So these guys come together, you've got your s orbital, and you've got 1 and 2 of the p orbitals, and they come together to make these nice little hybrid orbitals. These are sp2 hybrid orbitals. You'll notice that the lobe is a little bit bigger here because these guys are a third s character. So 1 out of the 3 atomic orbitals that mixed together was s, as opposed to sp3, where 1 out of 4 of the atomic orbitals was s, was sp3. So 1 out of 4, so that one's 25% s character. All right, so here they line each other up. Right, you've got these nice 3 hybrid orbitals, and they align themselves in a trigonal planar electron geometry. So make a triangle, and they're flat, 120 degrees apart. All right, so when these guys overlap, you can make different types of bonds. So the first bond we're going to talk about is a sigma orbital. So abbreviated with the Greek letter sigma. So these are head-to-head overlaps of the orbitals. So these can happen when you have unhybridized orbitals, so S to S or P to P, or a hybrid orbital to a hybrid orbital, or an S to a hybrid orbital. These are the first bonds that a molecule makes. So here we have ethane, which is CH3, CH3. You've got carbon with its its 4 sp3 hybridized orbitals. You've got the 1s orbital with the hydrogen bonding with the one of the sp3 orbitals, and then you've got this hybrid orbital left to bond with the other hybrid orbital of the carbon. So you have a head-to-head type of interaction here. These guys come together and make a bond. These are the strongest bond you can make. These are your single bonds that hold the atoms together. The next type of bond you can have is called a pi bond, abbreviated with the Greek letter pi, right? So these are a sideways overlap of orbitals. So you know how we talked about the sp2 orbitals that had an unhybridized p orbital? Well, this is where that unhybridized p orbital comes into play. So these guys are unhybridized, and they can have a parallel interaction with another unhybridized p orbital and make a pi bond that way. So it's drawn kind of weird here, but it's just the kind of side-to-side interaction. Obviously, they're not this close because there's a sigma bond holding them together and they're not right on top of each other, but you've got a side-to-side interaction here. So these are weaker than a sigma bond. So here's our Lewis dot structure of ethylene, which is C2H4. So I have a double bond holding together my two carbons, and then I've got CH sigma or single bonds. So anytime you see a single bond, that's going to be a sigma bond. All right, so here you've got your unhybridized 1s orbital with the hydrogen bonding with an sp3 hybridized carbon orbital. All right, so you've got 1, 2, and 3 hybrid orbitals making the sigma bonds or single bonds of the carbons. So we'll highlight those in orange. So 1, 2, 3, and then 1, 2, we'll use the same one as 3, holding together just the framework of that CH, or that ethylene molecule. But then you have a double bond, which I'll highlight in purple here. So that's your pi bond, right? That's this interaction here, that kind of side-to-side interaction. Everything else, this guy, and then holding the H's together, those are your sigma bonds. So you've got sigma bonds holding the framework together, then we get a pi bond bringing together that double bond. So anytime you see a single bond, that's going to be a sigma bond. Anytime you see a double or a triple bond, those guys are going to be pi bonds. Now these sigma and pi bonds can give different properties to your different molecules. So orbitals that form along the sigma axis, the sigma bond point, those single bonds, form between the different nuclei of the atoms. So they bond along the internuclear axis. So it's just between two atoms. You can rotate freely around these guys, right? There's nothing stopping you here. You've got nothing here or here, so they can just spin all around. So you have what we call free rotation around single bonds. So nothing stopping you there. If we look here at something that involves a pi bond or a double bond, you've got overlap above or below the nuclear axis. So you don't just have this sigma bond holding you together, you've got something above or below that. So that means is you can't spin freely around this internuclear axis. You've got something kind of holding you close together. So the way I like to think about it is if you take, it's kind of hard without seeing me, but take your two pointer fingers and put them together. You can spin around, all right? So that, your two fingers poking together represents a sigma bond or a single bond. If you take your pointer and your middle finger of your both hands and put them together, so like make a peace sign and then touch your fingertips together and try to spin that guy without moving your fingers apart, you have a lot harder time to do that. So this is why you have restricted rotation around double bonds and triple bonds, because you're held more tightly into place by that pi bond interaction. So this essentially gives rise to different structures. So here we have what's called cis-1,2-dichloroethene, where the chlorines are both pointing down, or they could both be pointing up. And then we have trans-1,2-dichloroethene, where you've got one chlorine pointed down and one pointed up. You can't just spin to interconvert these two structures. You have to actually break this bond and then reconfigure them and put them back together. So when you're looking at a molecule, for example, this is formaldehyde, it's usually the central atom that's going to make its hybrid orbitals. So with carbon, we're going to draw them all out here. We see that it has 1, 2, 3 areas of electron density. So that means we're going to need 3 hybrid orbitals. So that means we just make our 3 little lines. We've got 1 electron in each of our sp2 hybridized orbitals. And again, we chose sp2 because it has 1, 2, 3 hybrid orbitals. We need 1, 2, 3 hybrid orbitals because we've got 3 things around the carbon. So that's going to leave 1 unhybridized p electron. All right, so that's going to come together to make our pi bonds. So then we just match up unpaired electron to unpaired electron. We're going to make our sigma framework first. So we see between the 1s electron of a hydrogen and one of the hybrid orbitals of the carbon, that's going to make 1 bond. We'll draw him here. All right, then we've got another one between another 1s unhybridized orbital and a carbon hybrid orbital. That's going to be here, another sigma bond. And then with the oxygen, we have a hybrid orbital bonding with an unhybridized oxygen orbital. That's going to be one of your sigma bonds holding together the C and the O. And then that unhybridized p orbital is going to come together to make your pi bond. All right, so that's going to be your pi bond right here. All right, so we've got a sigma, a sigma, a sigma down here, and a pi bond here. All right, so it can get kind of messy, but once you just try to diagram it out, you can usually get to where you need to go. If we want to look at this molecule in more detail, again, we can see our carbon here as our central atom. Again, we chose the sp2 hybrid orbitals because, again, we have 3 areas of electron density around that carbon. So that's what's going to drive you to pick how many hybrid orbitals you need. So you've got an sp2 orbital bonding with the s orbital for hydrogen. You've got the same down here. Your other sigma bond is between an sp2 hybrid orbital and one of your unhybrid orbitals from oxygen. And then you've got your leftover p orbitals from carbon that were not hybridized, to make that pi bond. And then oxygen still has a lone pair. It's got 2 lone pairs, actually. All right, our final hybrid orbital we're going to talk about with the S and P is just the sp hybrid orbital. So this is formed by mixing 1s and 1p atomic orbitals, which is going to leave 2 unhybridized p orbitals. So you've got your 2 hybrid orbitals, your sp, and then 2 unhybridized p orbitals. So again, still 4 total orbitals. So these guys again come together with your s and your p. These guys are 50% s character. So you've got your 2 hybrid orbitals, and they make what's known as a linear geometry, so 180 degrees apart. So with these guys, because you have 2 unhybridized p orbitals, you can end up with 2 pi bonds with something with an sp hybrid orbital. So if we look at acetylene, which is C2H2, it's got its Lewis dot structure here. If we look at our hybrid orbitals, we see that it has if we look at this carbon, for example, we have 2 areas of electron density around it. So we know we only need 2 hybrid orbitals. So we make our sp hybrid orbitals, and again, that leaves 2 p orbitals completely unhybridized. So here you would make your bond, your sigma bond between your C and your H. On this side here, you make another bond between your C and your H here, and then you make a sigma bond between the two carbons. All right. And then that leaves you with two p orbitals that you can make a pi bond here and a pi bond here. So you've got one pi bond, two pi bonds, and then 1, 2, 3 sigma bonds in this molecule. Looking at this guy close up, you can just see exactly what we went through. You've got a sigma bond between the C and the H, and between the other C and the H, a sigma bond on the internuclear axis, so holding this molecule together. And then you've got two pi bonds with your unhybridized p orbitals that are 90 degrees apart. So these guys are perpendicular to one another. So one straight up and down, one is side to side. We can see the same with allene, which is a more complicated molecule. You've got two double bonds on the middle carbon. So again, let's look at hybridization here. It really is as simple as counting the things around it. So if we look at this carbon first, we see that we have 1, 2, 3 areas of electron density around him. So that means we're going to need 3 hybrid orbitals. So that means we're going to need sp2 here, right? So s is 1, 2 p's, 2, 3. Going to need the same for the right-hand side C, right? Because you've got 1, 2, 3 areas of electron density around him. So again, we can see our sigma bonds in blue here. So we've got 1, 2 down here, and 3 sigma bonds around the left-hand C. 1, 2, 3 sigma bonds around the right-hand C. If we look at the middle carbon, we see that it has 1, 2 areas of electron density, so 2 C's around it. All right, so that means we need 2 hybrid orbitals. All right, so that's going to be sp hybridized. So 1, 2, s and p. And again, that's what we see, right? We see our sigma bonds around our central carbon atom. So we've got 1 and 2 hybrid orbitals there. If we just have 2 sp hybrid orbitals, that means we have 2 unhybridized p orbitals on that central carbon. And on our outside carbons, we have 1 unhybridized p orbital each. All right, so again, we see that to make our double bond here, and we see that to make our double bond here. So this center carbon has 1, 2 unhybridized p orbitals, and our outside carbons just have 1. So again, at the outside, it looks really, really complicated, but if you just break it down and look at the things we already know how to do, which is count areas of electron density, and then, count to 3 or count to 2 or whatever, it starts to make sense. So the more you look at these, the more you diagram them, the easier it's going to get for you. So for these, just do some practice problems. I'll post some to Canvas, and that'll really help you start to identify these things. All right, so if you look back at your electron geometries chart, we've covered linear with sp hybridized orbitals, trigonal planar with sp2 hybridized orbitals, and tetrahedral with sp3 hybridized orbitals. But we have 2 more categories, right? There's trigonal bipyramidal, and then there's octahedral. But, we need more than just 4 orbitals to make those guys. So now we got to look at the d orbitals and start bringing those in with our hybrid orbitals. So the next one we're going to look at is the sp3d hybrid orbitals. So these are formed by mixing your s orbital, your 3 of your p orbitals, and 1 of your d orbitals. So this is going to make 5 hybrid orbitals together. So 1 plus 3 is 4, plus another is 5. All right, so again, they come together. You've got your 5 hybrid orbitals, all at the same energy level, and then this leaves you with 4 unhybridized d orbitals. All of these come together to make that happy trigonal bipyramidal shape we've seen when talking about something that has 5 areas of electron density around it. So again, looking at arsenic pentafluoride, AsF5, we see that arsenic has 1, 2, 3, 4, 5 areas of electron density around it, which means it's going to need to access that sp3d hybrid orbitals because it needs 5 of the same type of orbitals. So these guys come together and it's going to make 5 sigma bonds. And here that's going to be mixing of the sp3d hybrid orbital on the arsenic and just the unhybridized p orbital of the fluorine. Remember, we're only going to be looking at hybrid orbitals of central atoms here. So because it has 5 fluorines around it, it needs 5 hybrid orbitals, so sp3d. To get to our final shape, we need to access one more d orbital. So here we're going to have sp3d2 hybrid orbitals. So here we're mixing together one s, 3 of our p's, and 2 of our d's to give us a total of 6 hybrid orbitals. And again, just count your superscripts to get to the total number of hybrid orbitals. So that's going to give you 6 of the same energy level sp3d2 hybrid orbitals, and it's going to leave 3 unhybridized d orbitals alone. And that's going to give you this happy little octahedral shape with its 1, 2, 3, 4, 5, 6 things around it. So if we take a look at sulfur hexafluoride, SF6, sulfur has 1, 2, 3, 4, 5, 6 fluorines around it, 6 areas of electron density, so it has to access that sp3d2 hybrid orbital. So that's going to lead to 6 sigma bonds, again between that hybrid orbital of the sulfur, the sp3d2, and again the unhybridized f orbitals, to give you this happy little shape right here. Okay, so we've talked a lot about this, but how in the world is this going to look like as a problem? So here's one, and we're going to talk through it in steps. So keep these steps in mind when you're presented with a problem like this. So the question is, what orbitals are used in the bonding of acetaldehyde, which has the formula of CH3CHO? So how in the world do you start this? All right, so think about this for a minute, and then we'll talk through it together. All right, so anytime they ask you about any type of structure or bonding or anything and they give you a formula, the first thing you should do is draw a picture or draw a Lewis dot structure. So hopefully you've done that. If not, go ahead and try it now, and then we'll draw it together. All right, and again, the more you do, the easier these are going to get. When you have an organic type structure or that is kind of built on carbon, the way that the formula is written can usually give you an understanding of how it is bonded together. So this C here is bonded to 3 H's, which I've drawn here, so CHHH. And then that C is bonded to another C that has both an H and an O. So usually if the H is written before the O when it's next to a C, that means that both of those atoms are bonded to the carbon. If it's with an O and then an H, usually it's a C with an O and then an H on the oxygen. But again, you'll get used to it as the more you do. So if you monkeyed around with your electrons and how many you needed, you should have seen that this carbon would have been lacking an electron because you put the extra electrons on the oxygen, so you make a double bond there. Okay, so that's step 1. Always draw a picture, always check your Lewis structure to make sure it's the best one that you can possibly draw. Since all of these bonding theory things, rely on how many areas of electron density are around there, and it's very tied to the electron geometry, it makes sense that the second thing you should do is to assign electron geometries to your central atoms here. So take a second and then try to assign your electron geometries to each of your carbons. So this guy and this guy. So hit pause, do that, and then we'll talk through it together. All right, so let's look at the left-hand carbon. So to look at electron geometries, you again just need to count how many areas of electron density are around that atom. So this carbon, we have 1, 2, 3, 4 areas of electron density. So you can look back at your chart, or maybe you memorized it by now, but that correlates to a tetrahedral electron geometry. All right, so that's 1. So now let's look at this carbon, the right-hand carbon. So we can see that we have 1, 2, 3 areas of electron density around that carbon. And again, you can look at your chart, or maybe you just know that that correlates to a trigonal planar geometry. So now that we know our electron geometries and we know how many areas of electron density we have, we know that we need to have as many hybrid orbitals as we have areas of electron density. So it correlates directly to the electron geometry. So step 3 is to figure out your hybrid orbitals. So see what you can do with that, and then we'll check back in. All right, so let's look at left-hand carbon. So we have 4 areas of electron density, or a tetrahedral electron geometry. So that means we need 4 hybrid orbitals. All right. So we need an s, and we've got 3 p orbitals. So we need to blend together all 3 of those guys. So that means we're going to have 4 sp3 hybrid orbitals there. For the right-hand carbon, we need 3 areas of electron density, trigonal planar shape, so we need 3 hybrid orbitals for this guy. All right, so again, if I have my s and my 3 p orbitals, I only need 3 of these. So I'm going to start with the s and go to the second p. So this means I'm going to have 3 sp2 hybrid orbitals and then have 1 unhybridized p orbital left. So again, those are just for the carbons. For the left-hand carbon, I have sp3 hybrid orbitals. For the right-hand carbon, I have sp2 hybrid orbitals. So now we've got to look at the H's and then the O's. So I'm going to clean this up just a little bit, but think about what orbitals are bonding with the H's. So remember, with the hydrogen atoms, all you have is that 1s electron. So with hydrogen, all it's ever going to do is have that unhybridized s orbital. And then for the oxygen, we have a double bond here, right? So that means we've got a sigma bond and a pi bond coming together to form this CO double bond. So if you're keeping track, it's actually that sigma bond comes together with the hybrid orbital of the carbon, so an sp2, and then an unhybridized p orbital from the oxygen. Then the pi bond comes from the unhybridized p orbitals, again from the C and from the O. All right, so there's a lot going on here, but now with all of this, you can figure out what orbitals are overlapping to make, say, this bond specifically, and then this bond, and then this bond. So it's pretty cool that you can kind of see how this guy pieces together. So let's just try to diagram it out. So if we look at all the CH bonds on this left-hand carbon, we know that the H brings its unhybridized s orbital, and the carbon has sp3 orbitals. So each of these bonds, if I can draw 3 lines here, are between the s and an sp3 orbital, and that's what's bringing those together to make a sigma bond. If we look at this guy, we know that this carbon is bringing an sp3 hybrid orbital, and this guy's bringing an sp2 hybrid orbital. So this bond here is an overlap of your 2 hybrid orbitals to again make a sigma bond. Between the right-hand carbon with its sp2 hybrid orbitals, that guy is overlapping with the s unhybridized orbital of the hydrogen. And then with our oxygens, we have a sigma bond that is formed from the hybrid orbital of the carbon and the p orbital with the oxygen, and then you've got the pi bond forming from the 2 unhybridized p orbitals. So just by knowing the electron geometries and kind of what electrons are involved in the bonding, we can diagram out, what orbitals are coming together to actually make this molecule, which is actually kind of cool and kind of a powerful tool for us to visualize these. So that was kind of a long slide and a lot going on. So the next couple slides, I'm just going to give you again the questions you should be asking yourself that we did all in one slide to figure out this problem. So obviously, if you're faced with a question with a structure, draw a picture. You got to draw a Lewis structure. Then you've got to find your central atoms and assign hybridization. So again, we've done this before. The answer here was letter C. Based on its electron geometry, you can then figure out its hybridization. So it's tetrahedral, 4 areas of electron density. That gives you an sp3 hybridization. Again, just remember, count to 4. 1, 2, 3, 4. 1, 2, 3, 4. There's a typo on this slide. Carbon-2 is trigonal planar, not tetrahedral, so I've amended that here. So again, it has 1, 2, 3 areas of electron density around it, trigonal planar, so that would be sp2 hybridization. So 1, 2, 3 for its 3 areas of electron density, which leaves 1 unhybridized p orbital. If we look at our hydrogen atoms, we want to ask what is there for it to bond with. We know that's going to be letter A, an s unhybridized orbital, because that's all hydrogen has. So if we want to look at what is bringing together our 2 carbons to make a bond here, so we know it's just a single bond, so it has to be a sigma bond. More specifically, we know that it's the sp3 hybrid orbital overlapping with the sp2 hybrid orbital of the right carbon. Between carbon and oxygen, we see we have a double bond, so we've got 2 different types of bonding. We have a sigma bond in that internuclear axis, so holding them together in between the nuclei. So that's our sigma bond, and that's coming together between the sp2 hybrid orbital and the p unhybridized orbital of the oxygen. So we've got a sigma bond. Then we've got our second bond, which is forming between our 2 unhybridized p orbitals. So that is our CO pi bond. So that is, answer here is letter C, both A and B. So again, we can see it all drawn out officially, so we can see each of our independent overlaps and how they work together, but hopefully talking through it in both ways on the long slide and then very quickly through the multiple choice questions kind of shows you where you need to go. So again, this is a very powerful tool, and it's very easy to visualize and kind of picture in your brain what these orbitals look like and how they're coming together to overlap and to make these actual bonds. Remember, these are all based on the quantum mechanical approaches, so all the things that you can calculate. So the driving force for them to make all these bonds is that high overlap, which is a lower energy, stabilizing factor. So that's why these happen. So again, it can seem kind of complicated at first, but hopefully the more you read and the more you practice and the more you listen, it'll start coming together. But really, it's all just based on, how many areas of electron density you have, and then match that up with your specific hybrid orbital. And all we're going to go is up to 6 hybrid orbitals. So from sp all the way to sp3d2. That's all you need. So hopefully this was helpful, but again, I'm around for any questions you might have. Thanks, guys. Have a great day.